Nobody told you the truth about light years. Not really. They gave you the word. They gave you the number. They let you nod and move on. And that nod is the most dangerous thing you've ever done, because what you nodded at is a distance so fundamentally hostile to human existence that the moment you actually feel its size, something in you doesn't recover. A light year sounds like time. That's the first trap. The word year sits inside it like a quiet lie, and your brain, a 3-pound organ that evolved to track predators across a savanna, not measure the abyss between stars, grabs onto that familiar syllable and builds a picture that has nothing to do with reality. You imagine something manageable, something traversable. You imagine a year of travel, a long trip. Uncomfortable, maybe. Possible, certainly. You've been on long trips. You understand years. You've lived through dozens of them. But a light year is not a year of travel. It is not even close to a year of travel. A light year is the distance that light, the fastest thing in the observable universe, the thing that crosses a room before your neurons can register it happened, the thing that travels from the Earth to the Moon in just over a second, travels in an entire year, 365 days, 24 hours each. Light moving at nearly 300,000 kilometers per second for a full year, without stopping, without slowing, through the hard vacuum of space. That is 1 light year. That is the unit. That is the ruler being used to describe the universe. And the nearest star beyond our sun, a dim red dwarf called Proxima Centauri, that you will never see with your naked eye, is 4.24 light years away. Let that breathe for a moment. 4.24 years of light, not of driving, not of flying, not of anything a human body has ever done. 4.24 years of the fastest speed that physics permits. The universe is not using this unit because the distances are large. The universe is using this unit because any smaller unit would produce numbers so grotesque that the notation itself becomes meaningless. A light year exists as a concept because the alternative, expressing stellar distances in kilometers, generates figures that the human mind simply refuses to process as real. Proxima Centauri is approximately 40 trillion kilometers away. 40 trillion! The number sits there. It does nothing to you. Your brain absorbs it the way it absorbs a page of terms and conditions, KT, technically present, functionally invisible. This is the first truth that most conversations about space quietly skip over. The reason we invented astronomical units of measurement was not convenience. It was cognitive mercy. We built bigger rulers because the actual distances, expressed in human terms, are psychologically unbearable. And here is where it gets uncomfortable. Because even when we swap the unbearable number for the cleaner one, 4.24 light years instead of 40 trillion kilometers, we have not actually made the distance smaller. We've only made our picture of it more manageable. We have soothed ourselves with notation. The gulf between here and Proxima Centauri did not shrink when we named a new unit. We just stopped looking at it directly. We put on the equivalent of sunglasses and called it understanding. Now remove the sunglasses. The fastest human-made object ever launched is the Voyager 1 probe. 46 years after its launch, it has traveled roughly 23 billion kilometers, the farthest any human artifact has ever gone. 23 billion kilometers, a number that would have sounded impossible to every human who ever lived before 1977. And in those 46 years, traveling at speeds that required us to use the gravitational pull of Jupiter and Saturn like slingshots, Voyager 1 has covered approximately 0.002 light years, not 2 light years, not 0.2, 0.002. It has crossed, in nearly 5 decades of continuous travel, roughly 1/2000th of the distance to our nearest stellar neighbor. At this rate, Voyager 1 would reach Proxima Centauri in approximately 73,000 years. 73,000 years. That is longer than modern Homo sapiens have existed as a species. That is longer than the entire history of human language, agriculture, civilization, philosophy, science, and technology, combined, multiplied, and then multiplied again. And that is the journey to the closest star, not the edge of the galaxy, not a neighboring galaxy. The closest star, the one right next door, cosmically speaking, the one that in diagrams of our solar neighborhood appears almost touchably near. This is the thing nobody says plainly. The problem with space travel is not primarily that we lack the technology. The problem is that the universe has been constructed, if that is even a useful word, at a scale that seems specifically designed to prevent the kind of travel we imagine when we watch films about starships and warp drives and generations of explorers. The scale itself is the barrier, not the engineering, not the fuel, not the political will, the raw, physical, geometric fact of how far apart everything is. And there is something even stranger underneath that fact, something that most people have never been asked to sit with: light. The thing we use to measure these distances, the thing we have declared to be the universal speed limit, does not experience these journeys the way we imagine. According to relativity, a photon of light does not experience the passage of time. From the photon's perspective, if such a thing can even be said to exist, the journey from Proxima Centauri to your eye is instantaneous. The distance exists. The travel time exists. But for the thing doing the traveling at the speed of light, there is no duration, no waiting, no crossing. Which means the 4.24 light years between us and our nearest neighbor is not a distance that light struggles with. Light doesn't struggle with anything. Light simply exists here and then exists there. And the gulf between those 2 points is experienced only by things moving slower than light, which is everything with mass, every proton, every atom, every molecule, every cell, every human body. The distance that light crosses effortlessly is the distance that annihilates everything made of matter that tries to cross it. That asymmetry is the thing worth sitting with. We measure the universe in units derived from light's effortless crossing of distances that would require biological creatures tens of thousands of years, at best, to traverse. We have built our entire conception of cosmic geography around a traveler that experiences no distance at all, and then assumed that this geography should somehow be accessible to travelers who experience every meter of it. The universe is not hostile to us. It is something worse than hostile. It is indifferent in a way that makes hostility look like engagement. The distances are not barriers erected against us. They are simply what space is. They existed before life did. They will exist after. They require no maintenance. They do not need to keep us out, because nothing about them ever assumed we would try to get in. That is the first truth. And if it has settled into you with any real weight, you have already noticed the question it leaves behind. If this is the scale of the problem at 4 light years, at our closest neighbor, what happens when we start asking about the stars we can actually see with our naked eye? What happens when we ask about the ones we've named, the ones in our mythology, the ones that feel, on a clear night, almost close enough to reach? That question is where this gets genuinely impossible, because light, as it turns out, is not just a unit of distance. It is also the thing that sets the hardest limit physics has ever found. And everything that follows from that limit changes what space travel actually means in ways that most people have never been forced to confront. Given enough time, human technology always finds a way. That is not optimism. That is the demonstrated pattern of our entire history as a species. We looked at oceans and built boats. We looked at the sky and built planes. We looked at the vacuum of space and built rockets that escaped Earth's gravity entirely. Every barrier we have ever encountered has eventually yielded to ingenuity, investment, and the compounding momentum of scientific progress. This is not arrogance. This is the record. The arc of human capability bends, consistently and verifiably, toward the previously impossible. So when physicists talk about the speed of light as a limit, the reasonable response, the historically supported response, is to assume it is simply the next barrier, the next problem waiting for its solution, the next ocean waiting for its boat. That assumption is wrong, and the wrongness of it is not a matter of degree. It is structural. The speed of light in a vacuum is approximately 299,792 kilometers per second. For most of the 20th century, this number existed in physics textbooks alongside other large numbers, impressive certainly, but categorically similar to other records that had once seemed unbreakable. The sound barrier had seemed absolute until it wasn't. The idea of leaving Earth's atmosphere had seemed fantastical until it wasn't. So light speed, to a certain kind of thinking, was simply the next threshold. Difficult, extreme, but not categorically different from the ones before it. Here is the first crack in that thinking. When you accelerate an object, any object, its mass increases, not in a loose, approximate, theoretical sense, literally, measurably. An object moving at 10% of the speed of light is slightly more massive than the same object at rest. At 50% of light speed, the increase becomes significant. At 90%, it becomes severe. At 99%, the object's effective mass has increased by a factor of 7. At 99.9%, that factor exceeds 22. The closer the object gets to light speed, the more massive it becomes, and the more energy is required to accelerate it further. Not by the same amount each time, but by increasing amounts, escalating amounts, amounts that grow without ceiling as the speed approaches its limit. This is not an engineering problem. This is not a fuel efficiency problem. This is what the mathematics of special relativity produces, and it has been confirmed experimentally in particle accelerators around the world. Protons at CERN's Large Hadron Collider are accelerated to 99.99999% of light speed. And at those speeds, each proton behaves as though it has an effective mass approximately 7,000 times its rest mass. The energy required to push them that final fraction of a percent closer to light speed is astronomical, and protons are among the smallest particles that exist. Now consider a spacecraft. A spacecraft designed to carry humans would need, at minimum, life support systems, fuel storage, navigation equipment, structural integrity sufficient to survive the journey, and the human bodies themselves. Conservative estimates for a crewed interstellar vessel put the minimum mass somewhere in the range of tens of thousands of tons. Accelerate that object to 90% of light speed, and the kinetic energy required is already equivalent to thousands of nuclear warheads detonating simultaneously. Push it to 99%, and the energy requirement increases by another order of magnitude. Push it toward 99.9, and you are approaching energy outputs that dwarf the total annual energy consumption of the entire human civilization for a single launch, and you still haven't reached light speed. You have only approached it. The actual limit remains always exactly one step ahead. The mathematics does not allow you to reach it. At light speed, the mass of any object with rest mass becomes infinite. The energy required to accelerate infinite mass is infinite. The universe is not enforcing this limit through any physical mechanism you could dismantle or engineer around. The limit is embedded in the geometry of space-time itself. It is what space-time is. But here is where the story gets stranger, because the speed limit is only the beginning of the problem. Suppose for a moment that some future propulsion system, some technology we cannot currently imagine, manages to accelerate a spacecraft to a meaningful fraction of light speed, 90%, say. At that speed, something begins happening to time inside the spacecraft that is deeply unsettling to think about clearly. Time dilation. The faster an object moves relative to a stationary observer, the more slowly time passes for the moving object. This is not a trick of perception. It is not that the clocks seem to run slow. The clocks actually run slow because time itself is passing more slowly for anything moving at high velocity relative to something else. At 90% of light speed, time inside the spacecraft passes at roughly 44% of the rate it passes for someone remaining stationary. A year of travel on the spacecraft equals roughly 2.25 years outside it. At first, this sounds like a solution. It sounds like the universe is offering a compromise. Move fast enough, and you compress your subjective experience of the journey. The crew ages more slowly than the civilization they left behind. They arrive at a distant star having experienced fewer years than have passed on Earth. Science fiction seized on this immediately and built entire mythologies around it. The crew departs, the crew arrives. The crew returns older by decades while Earth has aged by centuries. Problem solved. Journey made. Stars reached. But look at what that solution actually requires: to compress the subjective journey to a manageable human lifespan, to reach a star 40 light years away in, say, 30 years of ship time. You need to sustain a velocity so close to light speed that the time dilation factor reaches the necessary ratio. The energy requirements at those velocities are not merely extreme. They are, by current physics, practically synonymous with impossible. The total energy output of the Sun over several years would need to be harnessed and directed efficiently, without catastrophic loss, into a single vessel's propulsion system. No known physical process produces energy at that density. No known material survives the forces involved. And this is without considering the question of what happens when your spacecraft, moving at that velocity, strikes even a single hydrogen atom. At relativistic speeds, a hydrogen atom becomes a high-energy particle impact. Sustained travel through interstellar space, which is not empty, which contains hydrogen, dust, and microparticles distributed at low but non-zero density, would require shielding with properties that no known substance possesses. The time dilation solution, in other words, solves the problem of human subjective experience while doing nothing whatsoever about the problems of energy, propulsion, and structural survival. It takes one impossibility and trades it for three others. And this pattern of apparent solutions generating deeper problems is precisely the pattern that has followed every proposed workaround to the cosmic speed limit. Ion drives, real, functional, tested, and so slow that reaching even Proxima Centauri would take tens of thousands of years. Solar sails, elegant, energetically free, and dependent on light pressure that becomes vanishingly weak long before any useful fraction of light speed is achieved. Nuclear pulse propulsion, Project Orion, the idea of detonating nuclear bombs behind a spacecraft to propel it forward, could theoretically achieve 3% of light speed, which sounds promising until you realize that 3% of light speed still means nearly 150 years to reach our nearest neighbor, carrying the political and diplomatic impossibility of launching nuclear devices in Earth's vicinity. Antimatter annihilation drives. Theoretically, the most energy-dense propulsion imaginable and currently producible by humanity at a rate of a few nanograms per year, at a cost, conservatively estimated, of tens of billions of dollars per nanogram. None of these are engineering problems waiting for better engineering. Each one collides at some point with a physical constraint that is not provisional. The universe does not have a waiting room where better technology can sit until it is ready to circumvent the rules. The rules are not arbitrary. The rules are what the universe is made of. What science fiction did, what it had to do to survive as a genre, was install a narrative escape hatch at precisely this point in the argument. Warp drives, hyperspace, jump gates, subspace, fold space. Every mechanism a different costume for the same unspoken admission. We cannot solve this problem, so we will imagine that the problem does not exist. We will invent physics that permits what actual physics forbids, and we will explore that imaginary universe instead of the real one. This is not a criticism of science fiction. It is an observation about what the genre reveals, collectively and by consensus, about the real universe. That the real universe, governed by the actual speed of light, is so fundamentally inhospitable to the kind of travel we want that our stories require magic to make it work. That magic has a name. In physics, it is called a violation of causality, and every proposed mechanism for exceeding light speed examined closely requires it, which is not a technicality, which is another way of saying time itself breaks. Effects precede causes. The sequence of events that makes reality coherent unravels. The cosmic speed limit is not the most discouraging wall. It is what follows from it that matters. Because once you accept that light speed cannot be reached, and that the distances involved are measured in units derived from light speed, a quieter and more devastating conclusion begins to form. The universe may not be difficult to traverse. It may be constitutively, geometrically, physically impossible to traverse. For anything made of matter, moving through time, subject to the laws that govern every particle ever observed. And if speed cannot solve the problem, the next question is obvious. The one that surfaces naturally when engineering fails, and physics says no. The question humanity has asked before, in other contexts, when the destination was too far for one person to reach in one lifetime. What if we simply sent more people? What if the journey itself became the world? That question leads somewhere darker than most people expect. The record is straightforward. In the year 1972, a group of researchers at Princeton University produced a formal study examining the viability of self-sustaining human habitats in space. The study was thorough. It considered population size, food production, psychological welfare, governance structure, and the minimum number of individuals required to maintain a genetically and socially stable community over multiple generations. The number they arrived at was 10,000. 10,000 people minimum to sustain a functioning human civilization in an enclosed, isolated environment without catastrophic degradation over time. The study was not alarmist. It was methodical. It produced a number, and the number was 10,000. Most proposals for interstellar generation ships discuss crew sizes between 100 and 1,000 people. That gap between the minimum for stable human civilization and the maximum that any realistic vessel design could carry is not a gap that has been resolved in the 50 years since the Princeton study. It has been noted, discussed, occasionally reframed, but not resolved. The record shows it open. Consider what the record contains about generational continuity aboard a long-duration vessel, a mission to Proxima Centauri, assuming propulsion technology far beyond anything currently operational. Say a sustained velocity of 1/10 the speed of light, which itself represents an engineering achievement requiring energy outputs orders of magnitude beyond present human capability, would require approximately 43 years of travel time. A single human generation. That sounds manageable until the record is examined more closely. The mission departs. The crew is at launch the mission. They carry its purpose, its training, its institutional memory, its emotional investment in the outcome. They chose this. They volunteered. They understand what they signed for. Their children did not. The first generation born aboard the vessel arrives into an environment they did not select, traveling toward a destination they will not live to reach under a mission mandate they inherited rather than chose. The psychological literature on coercion, institutional loyalty, and voluntary versus imposed purpose is extensive, and it says the same thing with consistent clarity. Humans do not sustain motivation, not across decades, not across generations, for goals they did not participate in selecting. The record on this is not ambiguous. It is one of the most replicated findings in organizational psychology. Purpose requires authorship. Meaning requires choice. A generation born into a mission is a generation that must be persuaded, continuously, to remain committed to an objective that was decided before they existed. There is no record of this problem having been solved. Not in military history, not in religious institutions, not in political dynasties, not in corporations. Every multi-generational human organization in recorded history has experienced drift, ideological, procedural, cultural, across generations. Most have experienced it catastrophically. The Catholic Church of the 15th century bore limited resemblance to the institution of the 5th. The Roman Empire of the 4th century would have been unrecognizable to the citizens of the 1st. Dynasties fracture, languages mutate, ideologies are reinterpreted until they invert. These are not failures of human ambition. They are features of human social architecture, documented across every civilization the record contains. Now place that architecture inside a sealed vessel. Remove external contact. Remove the possibility of institutional reinforcement from outside the crew. Remove the option of exit. A crew member who disagrees with the mission on Earth can leave. A crew member who disagrees with the mission in interstellar space cannot. The record on isolated populations without exit options is, again, not ambiguous. It trends consistently toward hierarchy rigidification, ideological radicalization, internal conflict, and eventually collapse or coup. These outcomes have been documented in isolated Antarctic research stations operating for 18 months, in submarine crews on extended deployments, in communes and intentional communities of every ideological variety. The timescale of a generation ship mission is not 18 months. It is not 5 years. It is, at minimum, several decades. And for destinations beyond Proxima Centauri, it is centuries. The record does not contain a single example of a human institution maintaining its founding purpose, structure, and values across 200 years of total isolation. Not one. What the record contains instead is the history of what happens to isolated human groups across long time scales. The bounty mutineers who settled Pitcairn Island in 1790, a group of 19 adults, descended into violence, murder, and social collapse within a decade. The Roanoke colony of 1587, 115 colonists vanished entirely within 3 years, leaving behind a single carved word and no further documentation. The record of isolated communities is, with very few exceptions, a record of fragmentation, of the original mission becoming unrecognizable, of the social fabric that seemed stable at departure, becoming something entirely different, or nothing at all, in the destination's absence. And Roanoke had land, had weather, had seasons and soil, and the grounding of a physical environment connected to the one its colonists had always known. A generation ship has corridors, recycled air, artificial light calibrated to simulate a day-night cycle on a planet that, as the mission extends, the youngest crew members have never seen and cannot meaningfully imagine. The psychological record on this specific condition, existence in an environment entirely manufactured and enclosed, without reference to any external natural world, is limited by the fact that no human has yet endured it for more than approximately 18 consecutive months. The International Space Station provides the closest available data point. Astronauts returning from extended stays aboard the ISS report with significant consistency, cognitive dulling, emotional dysregulation, difficulty with executive function, and a period of reorientation to gravity and open space that extends for weeks. These are individuals who chose their assignment, who trained for years, who maintained continuous contact with Earth, who knew their return date, and who spent a maximum of around 500 days in the environment. Their psychological and physiological data represents the best available record of what enclosed long-duration spaceflight does to a human being. The record on what it does after 500 days continues, but only in extrapolation. Because no data beyond that threshold exists, the record is silent past a certain point. That silence is not reassurance. That silence is the shape of the unknown. Now introduce a second cross-reference. The record of what happens to language. Linguists studying dialect divergence. The rate at which isolated human communities develop distinct speech patterns have documented measurable changes within 2 to 3 generations. Within 5 generations, dialects become sufficiently divergent that communication requires effort. Within 10, they frequently become mutually unintelligible. A mission of sufficient length would not merely experience cultural drift, it would experience linguistic speciation. The crew that arrives, if it arrives, may share no language with the civilization that launched them. The mission documents, the technical manuals, the institutional procedures written at departure may be unreadable to the crew at destination. Not metaphorically, literally. The record contains this pattern in every human language family ever studied. There is no exception. Here is the gap that the record does not explain. Proponents of generational ship travel acknowledge most of these problems. They are raised, addressed, and responded to with proposed solutions, careful crew selection, psychological support systems, governance frameworks designed for long-duration stability, educational programs to maintain mission purpose across generations. These proposals exist in the literature. They are detailed, serious, and in some cases mathematically modeled. What the record does not contain is any empirical test of whether they work. Not one. The proposals have never been trialed at anything approaching the relevant scale, duration, or conditions. They are, in the precise sense of the word, untested. And the history of untested social engineering, of institutions designed by architects who were certain they had accounted for human nature, is a history that the record treats unkindly. Consistently, predictably, and without exception, systems designed to manage human behavior across long timescales encounter variables that the architects did not model, always. The record does not contain a single counterexample. Cross-reference a third source, evolutionary biology. The human brain was shaped by approximately 300,000 years of selection pressure on the African savanna. It developed over that time a set of cognitive and psychological adaptations precisely calibrated to a specific set of environmental conditions. Social groups of 100 to 150 individuals, the Dunbar number, the maximum scale at which human social cognition operates with full relational tracking, environments with horizons, seasonal variation, physical danger from external sources, navigation of complex terrain, the ability to leave. These are the conditions under which the human brain achieved its current architecture. None of them exist on a generation ship. What exists instead is a social group that cannot grow beyond the vessel's capacity, with no external threat, no seasonal variation, no horizon, no terrain, and no exit. The mismatch between this environment and the cognitive architecture of the humans inside it is not a gap that can be bridged through cultural programming or mission indoctrination. It is a mismatch written into the genome. The brains aboard that vessel evolved for a different world. They will experience the generation ship the way any organism experiences an environment it did not evolve for, with stress responses that have no productive outlet, social instincts that have no appropriate target, and a pervasive low-level wrongness that no artificial environment has yet successfully eliminated. The record shows this. In every analog environment studied, in submarines, in Antarctic stations, in cave isolation experiments, in simulated Mars habitats, the record shows it clearly, quietly, and without any sign of a solution. The question the record does not answer, the gap that sits in the center of every generational ship proposal ever written, is this. Who decided that the generations born aboard would consent to the mission? Who decided on their behalf that they would accept confinement, purpose inheritance, and a destination they would never reach? And if they did not consent, if the second generation, or the third, or the fifth, decided that the mission was not theirs to carry, what mechanism aboard a sealed vessel traveling through interstellar space exists to adjudicate that disagreement? The record is silent on this. The silence is not accidental. What comes next? What the proposals inevitably reach for when generational continuity fails the test is the alternative that requires the humans not to be awake for the journey at all. The idea that if civilization cannot survive the crossing, perhaps biology can be paused for it, suspended, held in a state of waiting until the destination arrives. That answer is already waiting. And what the record shows about it changes the question entirely. The equation still exists. It has never been disproven. It sits in the published literature of theoretical physics, peer-reviewed and formally valid, describing a mechanism by which a spacecraft could travel between stars not merely faster than any conventional propulsion allows, but faster than light itself. The math is clean. The logic is internally consistent. The paper that introduced it was published in a respected journal and has been cited thousands of times since. The idea is real. The physics is real. And it does not work. It has never worked. It cannot work. And the reason it cannot work is the reason the entire century of human ingenuity aimed at this problem has produced the same result, dressed in different notation each time. Every escape plan begins in the same place. A set of equations that permits something extraordinary. Every escape plan ends in the same place. A physical requirement that the universe refuses to meet. To understand how that happened, how physics learned to promise what it cannot deliver, you have to go backward. The final image looks like triumph. In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a solution to Einstein's field equations of general relativity describing what he called a warp drive. Not a metaphor, not a science fiction shorthand, an actual mathematically derived, formally published solution. The mechanism worked like this. Instead of moving a spacecraft through space, which, as the previous section established, physics prohibits beyond light speed, the Alcubierre drive moved space itself. The spacecraft would sit inside a bubble of flat space-time. Ahead of the bubble, space would be compressed, contracting toward the destination. Behind the bubble, space would expand, pushing the origin point further away. The bubble and everything inside it would effectively surf a wave of space-time distortion, arriving at the destination without ever technically exceeding light speed. The spacecraft itself would remain at rest relative to its local spacetime. No relativistic mass increase, no time dilation paradox, no violation of causality. At least, not obviously. The equations permitted it. The concept was not the fever dream of a fringe theorist. It was rigorous. It was elegant. It was, in the precise language of mathematics, allowed. Step backward. Why did Alcubierre's solution permit what all previous engineering had prohibited? Because it was not engineering. It was geometry. The cosmic speed limit, the wall that destroyed every propulsion-based solution, applies to objects moving through spacetime. It says nothing directly about the movement of spacetime itself. Space is not subject to the speed of light. During the inflationary epoch of the early universe, the observable cosmos expanded at rates that vastly exceeded light speed, not because anything moved faster than light, but because the fabric of space itself expanded. Alcubierre found a way to describe this expansion and contraction of spacetime as a controlled, localized mechanism, a way to do intentionally at small scales what the early universe did spontaneously at cosmic scales. The math opened a door that physics had appeared to seal permanently. Step backward again. The door, examined closely, has a lock on the inside. To create the space-time distortion the Alcubierre drive requires, to compress space ahead of the bubble and expand it behind, you need energy. Not ordinary energy, not nuclear energy, not antimatter annihilation energy. You need negative energy. Energy with a value below zero, not a small amount of negative energy. The original calculations produced a figure for the total negative energy required to sustain an Alcubierre bubble of even modest size that was, in the notation of physics, on the order of the total mass energy of a body the size of Jupiter. But negative. Negative Jupiter masses of energy, not as a loose approximation, as a calculated minimum requirement. Negative energy is not imaginary. It is not a mathematical placeholder without physical meaning. It exists. In a quantum mechanical phenomenon called the Casimir effect, two uncharged metallic plates placed extremely close together in a vacuum experience a measurable attractive force, produced by the suppression of quantum vacuum fluctuations between them, an effect that can be described as a region of negative energy density. The effect is real. It has been experimentally confirmed. Negative energy is a physical phenomenon. It exists in quantities so vanishingly small that producing enough of it to fuel an Alcubierre drive would require collecting, concentrating, and stabilizing every Casimir effect occurring simultaneously within a volume of space larger than the observable universe by a conservative factor. This is not an engineering problem awaiting better techniques. The density of naturally occurring negative energy in the vacuum of space is so far below the required threshold that no physical process, discovered or theorized, bridges the gap. Step backward once more. When later physicists refined Alcubierre's calculations and developed modified versions of the drive, they reduced the negative energy requirement significantly. Harold White at NASA's EagleWorks laboratory published work suggesting that certain geometric modifications to the warp bubble could reduce the requirement to something closer to the mass energy of a small spacecraft in negative form. Still exotic, still beyond any known production method, but closer to the scale of a real physical object. This work was serious. It was conducted by a credentialed researcher at a government space agency. It received significant attention. It briefly, genuinely, felt like progress. Then the quantum instabilities arrived. A warp bubble of the Alcubierre type, analyzed from the perspective of quantum field theory rather than classical general relativity, exhibits a catastrophic problem at its boundaries. The interface between the distorted spacetime inside the bubble and the normal spacetime outside it accumulates high-energy particles, radiation in the broadest sense, that builds up over the course of the journey. By the time the bubble reaches its destination, the energy density at the bubble's leading edge may be sufficient to annihilate the spacecraft and the destination upon arrival. The warp drive in this analysis is not merely impractical. It is a weapon, a doomsday device that destroys its target upon contact. The mechanism that was supposed to deliver humanity to the stars would arrive as a catastrophic burst of radiation, and there would be nothing left of the vessel, the crew, or the destination worth examining. And even setting aside the radiation problem, the negative energy problem, the production problem, the stability problem, there remains the question of control. To initiate an Alcubierre bubble, you must first create the space-time distortion outside the spacecraft. But the spacecraft is inside the bubble. The controls are inside the bubble. The crew is inside the bubble. To shape and adjust a distortion of spacetime that lies entirely exterior to your position, you must send signals beyond the bubble's boundary, signals which, in the distorted geometry of the drive, cannot escape the bubble without exceeding light speed. The Alcubierre drive cannot be steered from the inside. There is currently no proposed mechanism for steering it from the outside. The most promising interstellar shortcut in the theoretical literature is a vehicle without a steering wheel, powered by a fuel source that does not exist, that would likely destroy its destination upon arrival. Step further backward, to the other door, the one that preceded Alcubierre by decades and seemed, in some ways, more fundamental: wormholes. Formally, Einstein-Rosen bridges, a feature of general relativity solutions identified by Einstein and Rosen in 1935, describing a topological shortcut through spacetime connecting two distant points. Not a path through space, but a tunnel beneath it. A fold in the fabric of the universe that places two locations in direct contact regardless of the distance between them in normal space. The mathematics of wormholes is older than the mathematics of warp drives, and it is similarly impeccable. The equations allow them. General relativity permits them. They appear in the solutions. A traversable wormhole, one large enough and stable enough for a spacecraft to pass through, requires, at its throat, a distribution of matter with negative energy density sufficient to hold the tunnel open against the enormous gravitational forces that would otherwise cause it to collapse in a fraction of a second. The quantity of negative energy required is, by current calculations, comparable to or exceeding what the Alcubierre drive demands. The same fuel source that doesn't exist, the same production impossibility, the same wall dressed in different geometry. And wormholes introduce a problem the Alcubierre drive does not. A traversable wormhole connecting two points in space is, under certain configurations of general relativity, equivalent to a time machine. The implications of this are not philosophical curiosities. They are active violations of causality, the principle that effects follow causes, and they generate paradoxes that most physicists believe the universe resolves by making wormholes impossible. Stephen Hawking formalized this intuition as the chronology protection conjecture, the idea that the laws of physics conspire at the quantum level to prevent the formation of structures that would permit time travel. The conjecture is unproven, but the pattern it describes of the universe systematically closing every door that would allow causality violations appears in the literature with uncomfortable regularity. Every shortcut leads to the same room. The pattern, examined across a century of theoretical physics, is this: the equations of general relativity are extraordinarily permissive. They allow warp drives, they allow wormholes, they allow closed time-like curves and negative energy distributions and exotic geometries of space-time that read like a catalog of science fiction concepts. The equations are generous. The equations do not impose impossibility directly. What imposes impossibility is quantum mechanics. The second great framework of modern physics, operating at scales below the classical description, where the smooth geometries of general relativity dissolve into a probabilistic foam of particle interactions, vacuum fluctuations, and uncertainty. Every proposed shortcut that general relativity permits runs directly into a quantum mechanical requirement, typically for negative energy or exotic matter, in quantities that quantum field theory cannot produce. The two great theories of physics, the ones that together describe essentially all observable phenomena, are in direct conflict at precisely the scale where interstellar travel would need to operate. This is the piece that does not fit the pattern. It should not be possible for both theories to be correct, and for their conflict to be so precisely located at the point where human ambition requires resolution. A universe in which general relativity and quantum mechanics were fully unified would have a clear answer. Either the shortcuts work, or they definitively do not. The universe we actually inhabit is one in which the two frameworks have never been reconciled, and the frontier of their irreconcilability happens to sit exactly at the boundary between the possible and the impossible for interstellar travel. That is not coincidence. That is not a gap waiting to be closed by a future paper. That is the shape of a problem that may not have a solution, because the problem is not a hole in the theory. The problem is that the theory, examined fully, returns the same answer from every angle. The universe permits these ideas mathematically and denies them physically, and the denial is not in the equations. The denial is in what the equations require. What the equations require does not exist. What the equations require may never exist. And the feeling that sits with that conclusion, the slow recognition that every door opened by human ingenuity leads not to freedom, but to a deeper, stranger wall, is the feeling that the next truth in this sequence makes unavoidable. The universe is not merely large. It is not merely fast. It is not merely indifferent to human lifespan or social stability. Something about its structure seems to have placed the things we most want to reach at exactly the distance where every mechanism we could imagine to close that distance breaks down. And there is a name for what it means when you are surrounded on all sides by walls that your own theories helped you find. That name is where this goes next. We assumed the universe was full of conversation. Not literally. Not voices. Not signals we had simply failed to tune into yet. But the broader assumption underneath that one, the one we never examined because it felt too obvious to question. We assumed that the universe, populated across its 100 billion galaxies by whatever intelligences chance and chemistry and time had produced, was in some fundamental sense connected. That the same physics governing our small corner of it governed every other corner. That the same light crossing our sky had crossed theirs. That the distances separating us from whatever else existed out there were large, certainly, but traversable in some ultimate sense. Bridgeable, if not by bodies, then by signals. If not by signals, then by the slow accumulation of knowledge moving at the only speed the universe permits. We assumed that separation was a problem of scale, not of structure. We were wrong about that, and the further we look into exactly how wrong, the more the universe begins to feel less like an ocean connecting distant shores and more like a collection of isolated rooms, each sealed from the others, each containing whatever life or intelligence happened to develop inside it, with no door between them and no way to build one. Start with the simplest version of the problem. A civilization exists on a planet orbiting a star 100 light-years from Earth. We send them a signal, a radio transmission, traveling at light speed, the fastest possible messenger. That signal arrives 100 years after we send it. They receive it, formulate a response, send it back. We receive their reply 200 years after our original transmission. The conversation has taken 2 centuries. Every exchange adds another 200 years to the lag. In the time between our question and their answer, the civilization that sent the question may not exist in any form continuous with the one that receives the reply. Languages will have changed, institutions will have changed. The specific individuals who composed the original message will be dead, along with their children, and in many cases, their grandchildren. The reply arrives not to the people who asked, but to their distant descendants, people connected to the original question by genealogy and archive, not by living memory or direct investment. This is communication at 100 light-years. The galaxy is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The further we looked at the math of interstellar communication, the more we found that the very concept of a conversation, 2 parties exchanging information, each responding to what the other has said, each building on the exchange in real time, is a concept the universe supports only within a radius that, cosmically speaking, is essentially 0. Conversation requires simultaneity. It requires both parties to be present, in some meaningful sense, at the same moment. The universe, structured as it is around a finite speed of light, makes simultaneity impossible at any distance large enough to matter. We looked at this, and we named it a technical challenge. We said, future civilizations will find ways to manage this. They will design communication systems that account for the lag. They will build relationships across centuries the way we build relationships across time zones, with adjustment, with patience, with tools calibrated to the delay. And then we looked further, and what we found at the next layer is harder to manage than delay. The universe is expanding. We have known this since Edwin Hubble's observations in the 1920s confirmed that galaxies are moving away from each other, that the space between them is growing, that the cosmos is not static, but dynamically, continuously inflating. What we understood less clearly for a long time, and what the discovery of dark energy in 1998 forced us to confront, is that this expansion is not slowing down, it is accelerating. The universe is not merely expanding, it is expanding faster and faster, driven by a force whose nature remains almost entirely unknown, that appears to be built into the fabric of space itself and grows stronger as space grows larger. The implications of this acceleration, extended across cosmic time, are among the most desolating conclusions physics has produced. Galaxies beyond a certain distance, the cosmic event horizon, currently located approximately 46 billion light-years away, are already receding from us faster than light. Not traveling through space faster than light, which relativity prohibits, but carried apart by the expansion of space itself, which is not subject to that prohibition. Light emitted today from a galaxy beyond the event horizon will never reach us. It will travel toward us for the entire remaining lifetime of the universe and never arrive. The space between us and that galaxy will grow faster than the light can cross it, for as long as space continues to accelerate. And space will continue to accelerate. The models say so. Dark energy, as best as we understand it, does not diminish over time. If anything, it intensifies, which means that the event horizon, the boundary beyond which no signal can ever reach us, is shrinking. Galaxies that are currently reachable, in principle, by sufficiently long-lived signals will eventually cross that horizon and become permanently inaccessible. Not inaccessible because of distance. Inaccessible because the space between us will be growing faster than light can travel, forever, with no mechanism to reverse it. The further we traced this forward in time, the quieter the universe became. In approximately 150 billion years, a timescale so vast it makes the current age of the universe look like a morning, the Milky Way and its small cluster of gravitationally bound neighbors will be the only structures remaining within our observable horizon. Every other galaxy, every other cluster, every other concentration of matter in the universe will have crossed the event horizon. Not destroyed, not gone, exactly. Simply permanently, irreversibly beyond reach. Unreachable by signal, unreachable by travel, unreachable by any means that physics, as we understand it, permits. Separated from us, not by distance in the ordinary sense, but by the ongoing, accelerating expansion of space between us, a separation that grows larger every second and will never stop growing. We paused here, looking at that timeline, and asked the question that the math makes unavoidable. If this is the future, what is the present? The present, it turns out, already looks like an early version of that future. The universe we can observe, the sphere of space from which light has had time to reach us since the Big Bang, contains approximately 2 trillion galaxies. Of those 2 trillion, the overwhelming majority are already beyond any practical possibility of contact, not because of distance alone, because of distance combined with acceleration, combined with the finite speed of light, combined with the finite lifespan of any civilization, technology, or signal-sustaining infrastructure. The subset of the universe that any civilization, including ours, could meaningfully interact with during its existence is not 2 trillion galaxies. It is a vanishingly small local neighborhood, already shrinking as the accelerating expansion carries more of the cosmos beyond the horizon. And within that local neighborhood, within the small portion of the universe where contact is not already physically impossible, we find the problem that has haunted astronomy since the mid-20th century. The one that physicist Enrico Fermi stated at a lunch table in 1950 with a simplicity that has never been adequately answered. If the universe is as old as it is, and as large as it is, and if the conditions for life are as common as they appear to be, and if intelligence develops elsewhere as it developed here, then where is everyone? We looked. We have been looking for decades, with radio telescopes scanning millions of frequencies, with optical SETI programs monitoring stellar flicker patterns, with systematic surveys of nearby stars for the kind of electromagnetic signatures that a technological civilization might produce. We have found nothing, not a single confirmed signal, not a single unambiguous artifact, not a single verified indication that intelligence has ever arisen anywhere in the universe other than here. The silence is total. We have interpreted this silence in different ways. Perhaps intelligence is rarer than we assumed. A statistical accident so improbable that it has occurred only once here, in this unlikely corner of this unremarkable galaxy. Perhaps intelligence arises commonly, but destroys itself reliably, through war or ecological collapse, or the development of technologies it cannot safely manage, before it has time to signal its presence. Perhaps intelligence arises and signals, and we have not been listening in the right way, or for long enough, or with sufficient sensitivity to detect the signals being sent. These are the interpretations that preserve the universe as a potentially inhabited place, a cosmos full of developing civilizations separated only by time and method. But there is an interpretation we tend not to stay with for long, because it is the most uncomfortable of all. Perhaps the silence is not the silence of civilizations hidden or destroyed. Perhaps it is the silence of the structure itself. Perhaps the distances involved, the light years, the expansion, the acceleration, the event horizon, ensure that even civilizations that survive, that endure for millions of years, that develop every technology their physics allows, find themselves in precisely the situation that our own analysis has produced, surrounded by a universe that is technically populated and practically inaccessible. Not because they have failed, because the geometry of space and time makes connection structurally, cosmically, permanently impossible at any scale that matters. We looked at this possibility and felt something shift, not dramatically, not like a revelation arriving with sound and light, quietly, the way understanding sometimes arrives, less like discovery and more like recognition. The universe we thought we lived in, the grand, connected, explorable cosmos of science fiction and collective imagination, began to look like something we had projected onto a much colder reality. The actual universe, examined closely, looks less like an ocean and more like a collection of sealed rooms. Each room contains whatever happened to develop there. Each room is governed by the same physics. Each room contains matter and energy and time. But the doors between the rooms are locked by something more fundamental than distance, or technology, or political will. They are locked by the speed of light, by the expansion of space, by the acceleration of that expansion, growing faster every second. By the hard geometric fact that the universe is larger than any signal can cross in any time frame relevant to the existence of the things doing the signaling. We are not at the bottom of this yet. Because all of it, the distances, the speed limit, the generational impossibility, the broken escape routes, the silence, the accelerating isolation, all of it is a description of a physical reality. It is what the universe is. What we have not yet confronted is what that physical reality does to the thing doing the confronting. What it does to a mind that evolved on a small warm planet under a yellow star, that built its entire architecture of meaning and possibility around the assumption of reachability, around the idea that what can be seen can be approached, that what can be imagined can be made real, that the horizon is not a wall. The horror is not what the universe is. The horror is what it means for the organism that has to know it. There is something missing from almost every conversation about space, and it should be impossible to miss. It sits at the center of every documentary, every textbook chapter, every late-night explanation of light years and parsecs and the cosmic web, and it is almost never named directly. The thing that is missing is this: you do not actually understand any of it. Not in the sense that matters. Not in the sense that would change how you move through your day, how you feel when you look at the night sky, how you register the distance between here and the nearest star. You have the numbers. You can repeat them. You can nod when they are presented to you. But the numbers have not reached the part of your brain that makes things feel real. And they never will. And almost nobody who talks about space ever says so plainly. This should be the first thing said. It almost never is. The human brain is, by every neuroscientific and evolutionary account we have, a survival instrument. It was built, shaped across hundreds of thousands of years of selection pressure, to model the world at the scale where modeling the world kept its owner alive. That scale has a ceiling. It has a floor. The floor is roughly the size of a berry, a track in soft mud, the movement of a shadow in peripheral vision. The ceiling is roughly the distance to the next water source, the edge of the territory, the horizon. Everything outside those bounds. Everything smaller than can be seen with naked eyes. Everything larger than can be walked across in a day or two. The brain handles not by modeling directly, but by using symbols, placeholders, compressed representations that allow the system to reference a concept without building a full experiential model of it. Numbers are the most powerful placeholders the brain has ever invented. They allow us to represent quantities that no human has ever directly experienced. You have never seen 1 billion of anything. Your visual system cannot resolve 1 billion individual objects. Your working memory cannot hold 1 billion distinct items. 1 billion is a symbol. It is a notation. It refers to a quantity that exists in the world but does not exist, cannot exist, as a direct experience inside the brain processing it. And because it is a symbol rather than an experience, it carries no emotional weight proportional to what it represents. $1 billion and $1 million produce different intellectual responses. You can do the division, you know one is 1,000 times larger. But the emotional texture of each, held in the mind, is surprisingly similar. Large, abstract, beyond personal scale. The difference between them, felt rather than calculated, is nearly nothing. This is called psychic numbing. It was described formally in the context of humanitarian disasters. Researchers found that the death of a single identified individual produced more emotional response, more charitable donation, more motivated action than the reported death of thousands of anonymous people. The brain does not scale its emotional response to the scale of the information it receives. Past a certain threshold, somewhere in the low hundreds, roughly the size of a social group, the brain evolved to track. The emotional weight of numbers flatlines, not gradually, sharply. One death produces grief. 100 produces a different kind of grief, more diffuse, but still present. 1,000 produces something closer to abstraction. 1,000,000 produces almost nothing that could be called a felt response. The brain has reached the ceiling of its emotional modeling capacity and switched from feeling to symbol processing. Now consider what space requires you to hold in your mind as a felt reality rather than a symbol. A light year. 9.5 trillion kilometers. The distance to Proxima Centauri, 4.24 light years, 40 trillion kilometers. The diameter of the Milky Way, 100,000 light years. The distance to the Andromeda Galaxy, 2.5 million light years. The diameter of the observable universe, 93 billion light years. These numbers do not produce proportionally larger emotional responses as they grow. They produce nothing emotionally distinguishable from each other. They are all, to the felt sense of any human brain, simply vast, unreachably large, abstract. The 93 billion light-year figure does not feel meaningfully different from the 4.24 light-year figure because both figures are so far outside the range of direct experience that the brain processes them using the same neural machinery, the symbol handling system, which is entirely divorced from the system that makes things feel real. This should have been named and confronted every time space is discussed seriously. It almost never is. And the reason it almost never is worth examining. Space documentaries, the genre, the aesthetic, the entire mode of presenting the cosmos to mass audiences are built on a specific emotional trick. They use music. They use slow camera movements across CGI representations of nebulae and star fields. They use a narrator's voice calibrated to convey reverence and awe. They show Earth from orbit, small and luminous against blackness, and they let the image carry an emotional charge that the audience interprets as understanding. You feel something watching those images. The feeling is real. The music is affecting. The visual scale, the planet small against the void, produces a genuine response in the emotional system. And that genuine response is consistently, almost universally, mistaken for comprehension. You felt something, so you believe you understood something. But what you felt was the image. What you felt was the music. What you felt was the accumulated cultural weight of decades of similar imagery telling you that this is what awe at cosmic scale feels like. You did not feel the distance. You did not feel the 4.24 light years. You felt a picture of space, which is not the same thing, which can never be the same thing, and which is separated from the actual reality it represents by precisely the gap that no human brain can close. This pattern has appeared before, consistently. In every domain where reality operates at scales, the human perceptual system cannot directly engage. The scale of geological time, billions of years of Earth history, is something every educated person knows about and almost nobody feels. You know the dinosaurs died 66 million years ago. You know anatomically modern humans appeared 300,000 years ago. You can calculate the ratio. You cannot feel the ratio. The 66 million years does not feel longer than the 300,000 years in any way that would change how you think about either. They are both simply long, ancient, past. The felt difference between them is essentially zero, even though the actual difference is a factor of 220. The same failure occurs at the subatomic scale. You know that the atom is mostly empty space. You know that if the nucleus of a hydrogen atom were enlarged to the size of a marble, the electron would orbit it at a distance of roughly a kilometer. You know this. You cannot feel it. The marble and the kilometer do not assemble themselves into a genuine felt model of atomic structure inside your brain. They remain symbols. The reality they are meant to convey, the fundamental emptiness of solid matter, is information you carry without any experiential access to what that information describes. What is suppressed in these conversations, what is consistently, almost strategically, left unexamined, is the implication of this limitation for everything else being said. If the brain cannot emotionally model the distances involved in space travel, it cannot genuinely evaluate the barriers those distances create. It hears that Proxima Centauri is 4.24 light-years away, and it produces the same response it would produce to any very large number: a brief impression of vastness, followed by acceptance, followed by processing the next piece of information without carrying any felt weight forward. The brain moves on. It always moves on. The number does not accumulate into dread. It does not settle into the body the way that a real barrier, a locked door, a flooded road, a physical wall, settles into the body. Real barriers produce frustration, urgency, the motivated search for alternatives. The cosmic barriers produce a nodding familiarity that never reaches the emotional system at all. This is why the dream of space travel survives intact despite everything the previous sections of this documentary have established. It is not that people have heard the arguments and rejected them. It is that the brain has processed the distances as symbols, processed the barriers as symbols, processed the impossibilities as symbols. And symbols do not produce the behavioral and emotional responses that real, felt, understood obstacles produce. The warp drive and the generation ship feel equally plausible to the brain that cannot genuinely model either distance, because both are operating entirely in the symbolic register, where plausibility is not tested against felt reality, but against narrative convention. We've seen enough science fiction to have a symbol for interstellar travel, and that symbol is no more or less emotionally compelling than the symbol for the problem it is meant to solve. The further you follow this, the more the suppression reveals its own shape. We have built an entire civilization of space aspiration. Museums, agencies, films, telescopes, documentaries, on the implicit promise that understanding these numbers means something, that holding the figures in your mind constitutes a relationship with the reality they describe, that knowing the distance to Andromeda is a form of connection to Andromeda, and the thing nobody says clearly, the signal that keeps being overlooked, is that it isn't. Knowing is not feeling. Symbol is not experience. The number in your mind and the reality in the universe are separated by a gap that the brain, structured as it is, cannot cross. Not with better education, not with more powerful visualizations, not with any tool that operates by adding more information to a system that has already reached the ceiling of its capacity to convert information into felt reality. The universe may be comprehensible in notation. It may be entirely, permanently, structurally incomprehensible in experience. And those are not the same thing. The difference between them is not a matter of intelligence or curiosity or effort. It is a matter of what the brain is, what it was built for, what it can do, and what it cannot, regardless of how much it knows. That gap between the universe as symbol and the universe as felt reality does not stay still. The moment you genuinely hold it, even briefly, even partially, something in the way you think about humanity's future in space begins to shift. Not because the physics changes, because the question changes. The question is no longer whether the distances can be crossed. The question is what it means for a species to orient its ambitions around a reality it cannot emotionally access, toward destinations it cannot genuinely feel, across distances it will never truly understand. That question about what humanity is and what it is for in a universe structured like this one is the place this has been building toward all along. What does it mean to be home? The question seems simple. Home is where you live. Home is the place your body returns to, the place calibrated to your needs, the place that carries the accumulated texture of your existence. Home is familiar. Home is survivable. Home is, in the most basic biological sense, the environment that did not kill you. The answer feels obvious enough that the question barely seems worth asking, but ask it again, from further away. What does it mean to be home when home is the only place in the universe you can survive? Not the only place you prefer, not the only place you have built infrastructure, the only place, the single location within the cosmic volume of space, where the atmospheric composition, gravitational force, radiation environment, temperature range, and biological resources combine to sustain the organism you are. What does that make home? Not a preference, not a starting point, a constraint, a boundary drawn by physics around the entire possible geography of your existence. Is that still home, or is it something else? Try to answer that and something shifts, because the word home carries warmth, safety, belonging, chosen return. But a place you cannot leave is not chosen. A place you cannot leave is not returned to, because departure was never an option. The warmth of the word sits uncomfortably against the coldness of the condition it now describes. An entire species across its entire history, confined to a single world, not by failure of ambition or technology, but by the structure of the reality surrounding it, confined by distance, by time, by the speed of light, by the expansion of space, by the architecture of its own cognition, by the shortness of its lives, by the impossibility of every escape plan physics has allowed it to imagine. If that is home, what does the rest of the universe become? Decoration, perhaps. An enormous, ancient, intricate decoration. A surrounding that can be observed, measured, analyzed, mapped in extraordinary detail, and never entered. The night sky, examined from this position, is not a frontier. It is a window. And windows, however beautiful, however perfectly transparent, are not doors. You can press your face against a window for a lifetime, and the world on the other side will not become reachable. The glass remains. The separation remains. The view remains astonishing, but the view is all it is. And here is where the spiral tightens. Because if the night sky is a window and not a frontier, what has humanity been doing for the last several thousand years of stargazing? Every culture that has ever existed has looked at those points of light and built stories around them. Navigation systems, religious cosmologies, mythologies of gods and heroes written across the constellations, scientific frameworks that eventually revealed what the lights actually are, nuclear furnaces at distances so extreme the brain cannot model them, and then continued building aspiration around them regardless. We looked up and we said, that is where we are going, not as a plan, as a conviction, as a definition of what our species is and what it is for. The stars are not decoration to us. They are destination. They are evidence that the universe is larger than here, and that larger than here is something we are meant to reach. What if that conviction was always the wrong response to the right observation? The observation was correct. The universe is incomprehensibly larger than here. That is accurate. What may have been incorrect is the assumption that larger implies accessible, that visible implies reachable, that the existence of stars at vast distances constitutes an invitation to cross those distances. The universe did not place stars in the sky as waypoints. The universe did not arrange its geometry around the ambitions of the organisms that developed on one of its several trillion planets. The stars appear where they appear because gravity and nuclear physics and the history of the cosmos placed them there, at distances determined by no logic that takes human biology into account. They look reachable because human eyes evolved for a world where visible things were reachable. That is what eyes are for, tracking objects at distances where intervention was possible. The eyes that now look at stars 4 light years away are the same organs that once tracked prey across a savanna. They were not designed for this. They report reachability because reachability is all they know how to report. So what does it mean that we look up and feel, still, that pull? That the sensation of wanting to go there persists in the body even after the mind has understood why it cannot. Every person who has ever stood under a clear sky and felt that specific longing, not just curiosity, but pull, the physical sensation of wanting to be elsewhere in the cosmos, is experiencing something that evolution produced for entirely different reasons. The brain that tracks distant objects and feels motivated to cross to them was selected for on a planet where crossing to distant objects was possible. That brain now applies its crossing motivation to objects it cannot cross to, and the feeling is identical. The longing is real. The longing is just misaddressed. It evolved for here and has been pointed at infinity by a species that made the mistake of understanding how large infinity is. And every human who ever lived felt some version of this. Not just astronomers, not just explorers. Every person who looked up on a night with no cloud cover and experienced the specific disorientation of feeling small beneath something so much larger than themselves. That experience, repeated across every culture and every century of human existence, is not a failure of understanding. It is the organism responding to the only honest information the universe ever offers it directly. You are here. And there is an enormous amount that is not here, and you cannot reach any of it. The stars communicate this clearly. They have always communicated this clearly. The message was never invitation. The message was scale. The message was, This is how large the container is in which your island floats. Every human who ever loved someone did so here. Every grief, every discovery, every cruelty, every act of extraordinary generosity, every language ever spoken, every structure ever built, every idea that changed the course of civilization, all of it occurred on a single body of rock and water and atmosphere, held by the gravity of a single unremarkable star, separated from the nearest other star by a void that takes light itself 4 years to cross, separated from the nearest galaxy by a void that takes light 2.5 million years to cross, surrounded in every direction by distances that no technology humanity has ever produced or imagined, has come within a factor of thousands of bridging. This is not the backdrop against which human history occurred. This is the condition of human history. The distance was always there. The impossibility was always structural. The stars were always this far. We simply did not have the instruments to know it until recently, and knowing it has not changed the feeling. And changing the feeling may be beyond what any amount of knowledge can accomplish. What then do we do with the looking up? What does the gaze mean when the thing being gazed at is permanently beyond reach? Not because we have not tried, not because we have not thought hard enough or built well enough or lasted long enough, but because the universe was assembled at a scale that treats the distance between here and there as ordinary and treats us, with our short lives and our massive ships and our elegant mathematics and our profound, persistent, misaddressed longing, as something too small to be a variable in its calculations. The stars look close only because human eyes evolved on a tiny world beneath them. And every night that world turns and the stars appear again exactly where they were, exactly as bright, exactly as unreachable as they were for every human who looked up before us and felt the same pull and understood, finally, the same thing. Not that the journey is difficult, that the distance may be the truth, that the universe is not withholding the stars from us, that the universe simply does not organize itself around what we want to cross. We are here. We have always only been here. And the terrifying, gorgeous, unbearable reality is that here was always surrounded by an infinity that looked, from the inside of our small eyes, on our small world, beneath our small yellow star, like it was only a matter of time before we reached it. It was never time. It was always distance, and the distance does not end.